Hi everybody. In this video, we're going to examine a historical problem, which is perhaps the first known problem of graph theory and sort of launched the subject. So this is called the Seven Bridges of Konigsberg, or the Konigsberg Bridge problem, and this problem was known way back in the 1700s. So Konigsberg was this city in the 1700s. It was a city in Prussia. Now it is the city Kaliningrad that's in Russia. And so here I have a map, a historical map of the city, and you'll notice there are these rivers in the city. That river splits here and goes down this way, and it comes up this way and connects there. There's a little canal, and then this river goes that way. And so this river that's in Konigsberg separates the land masses of Konigsberg, and it makes these, what do we have here? 4 land masses of Konigsberg that this river splits it up into. And there were several bridges crossing this river. So here's a different map of Konigsberg with the bridges highlighted. So here's our 4 land masses again, and these 7 bridges, so hence the 7 bridges of Konigsberg. Now the problem was to determine if there was a route one could take walking on foot, walking across these bridges, a route that one could take that crosses each bridge exactly once. You didn't have to end up where you started. You could end up at a different landmass, but nevertheless, the question was, can we cross each bridge exactly once, right? Can we hit every bridge and not double up on any bridge, was the question. So this problem, while many people knew the answer was no, there shouldn't be a way to do this, and there were a few arguments for why this should be true, it wasn't really mathematically formalized until Leonhard Euler wrote a proof in a journal at the time. So I want to read, you can find this in our text, but I want to read this passage from the journal article that Euler submitted. So it goes like this. In addition to that branch of geometry which is concerned with magnitudes, and which has always received the greatest attention, there is another branch, previously almost unknown, which Leibniz first mentioned, calling it the geometry of position. This branch is concerned only with the determination of position and its properties. It does not involve measurements nor calculations made with them. It has not yet been satisfactorily determined what kind of problems are relevant to this geometry of position, or what methods should be used in solving them. Hence, when a problem was recently mentioned, which seemed geometrical, but was so constructed that it did not require the measurement of distances, nor did calculations help at all, I had no doubt that it was concerned with the geometry of position, especially as its solution involved only position, and no calculation was of any use. I have therefore decided to give here the method which I have found for solving this kind of problem as an example of the geometry of position. So here we have Euler describing this branch of geometry as they saw it, as Leibniz saw it, as Euler is seeing it, a branch of geometry which is not concerned with distances. Measurements of distances, angles, things like this were not relevant to the problem and didn't help in solving it. And so this was seen as a totally different branch of geometry, and they called it at the time the geometry of position. So we're only concerned with positions and not distances, things like this. So this is our first hint of graph theory. This geometry of position would later be known as graph theory. So examining this problem, right? Can we cross each of these 7 bridges exactly once? Euler gave a proof of the negative. No, in fact, we cannot. And here is a proof of it. So let's talk about a proof, how he was able to solve this problem and convince everyone that it was, in fact, a negative. It was not true. So in order to do this, I have another graph or another diagram here. that sort of more accurately describes the position. We kind of throw out all the extraneous stuff. We don't need those buildings or anything in them. What we really need to keep track of are the land masses, here with capital letters A, B, C, and D, and the bridges, each of lowercase letters A, B, C, D, E, F, and G. All right, so how did Euler's proof work? Like he said, it doesn't involve distances, and in fact, this was the big hint that this wasn't a strictly geometrical problem, or at least not a normal geometrical problem. Is it didn't really matter how long these bridges were, or what the distances were between land masses. All we cared about was the positions of the land masses of the bridges. What did the bridges connect? Which two land masses? Things like this. This is graph theory. So what did Euler's proof look like? Well, Euler noticed the following. He noticed if we want to cross each, well, I guess I'll start with this, that Euler, instead of viewing this as a graph, or as really this is a multigraph, I'll say more on that later. Instead of viewing this as a graph, he said a solution to this problem could be given as a sequence. So that is, or I'll say a solution. So that is a route that crosses each bridge exactly once. A solution would be given by a sequence of land masses. Right, that's one way to give a route, is to give a sequence of land masses, so these capital letters. So each land mass in the sequence, so let's say a land mass given in the sequence tells us that we take a bridge into the landmass and then out of the landmass. So this would correspond to taking two bridges, one to go in and one to go out. And so that would be if this occurs on the inside of the sequence. This would be the case. And so since we want to visit each bridge, we want to cross each bridge exactly once, such a sequence would involve 8 bridges, right? So sort of think about it as the gap between two land masses as you progress in the sequence. So like if I have a sequence like, let's say A, B, D, C, for instance, this would mean I would start at landmass A. I would take this bridge to go to B. It could be either little a or little b. Euler is kind of saying it doesn't exactly matter which one you take. A to B, and then we would take the bridge from B to D, and then we would take the bridge from D to C. And so this if we have 4 land masses in the sequence, that would correspond to 3 bridges, right? One less bridge than the number of land masses that are in the sequence. We can sort of think of this as a path, in terms of graph theory, as a path, and there's one less edge than the number of vertices. So more on this in a little bit. Anyway, so Euler says, okay, if we want to cross each bridge exactly once, then a sequence that solves this, so a solution that solves this, would consist of 8 terms, right? 1 for each landmass, and then so there would be 7 bridges in total to get between landmasses. So then what Euler did is he examined each landmass. So how many times would A have to occur? How many times would B, C, and D each have to occur? Now A has 5 bridges coming off of it. And so this would mean that we would need to see A 3 times in the sequence in order to cover each one of the 5 bridges that either go into or out of it. It would need to occur 3 times. So A would need to occur 3 times. And let's examine the other ones. Let's see, B has 3 bridges going into or out of it, so it would have to occur twice. And same with C and D. Each of those would also have to occur twice in the sequence. So B, C, and D would each have to occur twice. So that gives A 3 times, each of these 2 times, so that would give 9 terms in the sequence. So there must be 9 total terms. Of course, this is a contradiction, right? Noting these, we can sort of think about this as degree, looking at the degrees of each landmass. We would need 9 total terms to cover the bridges, but any solution is exactly 8 terms to cover the 7 bridges. And so this is a contradiction. And so no such solution can exist. So no solution exists. And that was essentially Euler's proof and the first example of what they were calling the geometry of position. So what are we concerned with? We're not just concerned with this Konigsberg bridge problem. We examine it because it's historical. It's the first, example of a graph theoretic problem that's solved in a way that doesn't involve measuring distances or angles or anything like this. Sorry about that. So what exactly are we getting at? So what I'm going to do here is I'm going to take, maybe you've already seen this and you can envision in your mind, but I'm going to take this Konigsberg bridge problem and I'm going to produce a graph from this. And actually, strictly speaking, I'm producing a multigraph. So for each landmass, I am going to denote it with a vertex. So I have A, C, all right, that'll be a little bit better, D, and B. So there's my 4 land masses, and then I will connect vertices if there's a bridge between those land masses. So A and C, I actually get 2 edges. This is why this is strictly a multigraph, because we allow what we call parallel edges. So 2 vertices can have more than 1 edge between them. This is not strictly a graph. We call it a multigraph. That's okay. We can still examine this problem in the case of a multigraph. So A has 2 bridges that connect to B. A has 1 bridge that connects to D. And let's see, D and C connect via bridge little g. And then B and D also connect via bridge F. So I can even put the labels of the bridges in there. B, G, E, and F. And so there's another way to see this Konigsberg bridge problem is with this multigraph. And then the question would be, can I find so what are we thinking here? It's not necessarily a path because I'm allowed to hit every vertex more than once, right? I would need to if I want to cross all the bridges. So this would be an example of a trail. So the question is there a trail in this multigraph? And remember, trails, you can't use an edge more than once in a trail. That would be a walk if you have a trail that crosses the same bridge more than once, the same edge more than once. That'd be an example of a walk and not a trail. So is there a trail in this multigraph that contains every edge? In the question, we could use the same solution that Euler did. The answer is no, we can't. And so what we'd like to do is extend this problem to graphs, to multigraphs, and figure out, just given any graph, given any multigraph, can we find what's called an Eulerian trail. So a trail that crosses every edge exactly once. It contains every edge exactly once. Or there's another variation of this, which is not just an Eulerian trail, but rather an Eulerian circuit. So can we do the same thing, cross every edge exactly once, and end up where we started? So this is 2 concepts, Eulerian trails, and Eulerian circuits. So in the next video and in the next section of the text, we get into Eulerian circuits and Eulerian trails, and we prove theorems which this is actually a quite easily solved problem to figure out a characterization for graphs. So what properties of a graph have to be there in order to guarantee it has an Eulerian trail or have an Eulerian circuit? How do we know if it does based on properties of the graph? And as we saw with Euler's solution, it depended on how many, right? He used the fact that, there were 5 edges coming in or out of A, and so it would need to occur 3 times in the sequence. He was looking at the degrees of the vertices. And so it shouldn't come as too much of a surprise that this characterization for when an Eulerian trail or an Eulerian circuit exists depends on the degrees of the vertices. So more on that in the next couple videos. See you there.